Hello everyone. This work is together with Weichen Zhang, Handong Chen, Lin, Xuehuai, Lili Wang from Beihang University. In highly cluttered multi-object scenes, objects to be selected together are seldom clustered together naturally, making it difficult for volume selection. Design a way to rearrange them, so that objects that users want to select together are more clustered. In the related work of single object selection, Owell et al. Present a virtual, flexible pointer that allows a user in a 3D environment to point more easily to fully or partially obscured objects. A dynamic object rating method was proposed to assist 3D object selection and increase selecting accuracy. Delamar et al. Proposed multi-finger bubble, a new variation of the 3D bubble cursor, which can select multiple target objects with the user's multiple fingers. Wu et al. Proposed EEBIA, an efficient and ergonomic big arm for distant object manipulation based on elbow angle mapping optimization. Sidinmark et al. Introduced outline pursuits, which extends a primary pointing modality for gaze-assisted selection of occluded objects. In the related work of multi-object selection, Zhang et al. Presented a new 3D user interface for selecting an arbitrarily shaped region of interest, ROI, in virtual reality. Stenholt et al. Explored various selection tools, such as a brush, a lasso, and a magic wand for large-scale multi-object selection. Yu et al. Presented a family of 3 interactive context-aware selection techniques, CAST, for analyzing large 3D particle datasets, which improves usability and speed of spatial selection in point clouds. In the related work of object group selection, De Barba proposed the LOP cursor, a metaphor that shows possible suitability for group selection with its two-legged cursor design, one for selection and the other for grouping. Felice et al. Created sticky lines, a tool that treats guidelines for object alignment. Xu et al. Present 4 interaction techniques for 3 degrees of freedom translational alignments. The traditional way of selection is almost to carry out only one round of batch selection, and then several local modifications. Batch selection is efficient but only performed once, while inefficient single selection is performed far more times. We need a new pipeline to regulate the number of batch selections and individual selections. Accordingly, we need to define what users and computers need to do at each stage of the new pipeline. The object's distribution in figure A look more complex than that in figure B, but why? We need an accurate mathematical way to measure the complexity of the distribution of objects in the scene. Batch selection alternates with object rearrangement, with new batch selection opportunities generating. The probability of objects in the scene being grouped into M groups is recorded with M-dimensional vectors P. The value of P is dynamically updated automatically when the user actively makes the grouping choice. Following 2 principles, update the probability vector P for each object around the center of the object that the user has actively grouped. Multiple centers. The probability vector of the outer object is only affected by the probability vector of the inner object. According to the probability calculated previously, rearrange the position of each grouped and ungrouped object in the original scene, following 3 principles, decentralized group centers, to be performed on the next page. Negative correlation between the probability and the new distance from the object to the group. No overlapping. Divide the space into discrete 3-dimensional cube grids, which contain at most only one object in a grid. The original scene is regarded as a large cuboid. These cores are distributed on the outer surface, edges and vertices of the large cuboid to maximize the distance between different groups. The new position is the weighted average of M cores, and the weight is the probability. The order is the same as that of probability calculation. If the target grid isn't empty, look for a nearest empty grid. Significate the probability vector P with mathematical processing to avoid many objects aiming at a same grid. We define the scene complexity as a value in the interval 0, 1, from small to large, representing the scene from complex to simple. After mathematical derivation, we conclude that the complexity of the scene can be described by the formula in B. We used a 3 times 3 times 3 repeated measures within subject user study design. Consider the advancement and relevance of the comparative method. We tested 3 group selection methods: multifinger bubble, CC1, point and volume based selection, CC2, and our PwP method, EC, with 3 levels of group number. 3 orderedness levels S. Our PwP method supports the integration of any effective batch selection method. In this user study, to ensure consistency with CC2, we used a cube-shaped batch selection volume. The total number of the candidate objects was the same. We set it as 120 in the study, for all conditions. For each method, each group number level, and each orderedness level, when all objects were selected and grouped, the participant completed a trial. For one group selection task, a participant should finish 27 trials. In total, we conducted 18 times 27 equals 486 trials. The user study procedure is shown in the figure. Each participant participated in the experiment for 9 days. On the first day they arrived at the experiment site. They signed the information sheet. Then, we explained and showed them the operations of 3 group selection methods. After that, they conducted technical training to familiarize themselves with the methods. Meanwhile, we assigned each participant a specific order of the 3 methods. The balanced Latin squared determined the order. We counted the following 2 objective metrics: completion time, the time it took for the participant to complete a trial; number of operations, the user operation times during each trial. A complete selection and grouping are recorded as one user operation. Despite the above metrics, we also recorded the single object and multi-object selection times for both CC and EC methods, and the number of conducting PwP modules for the EC method. For subjective metrics, we used the standard NASA TLX questionnaire to measure the task load, and the system usability score, SUS, to measure the usability of the methods. Each participant filled out the questionnaires after they completed the task. We conducted a multivariate analysis of variance, MANOVA, to analyze the effects of 3 independent variables: group selection method, number of groups M, and the layout orderedness S, on the performance of the above metrics. A significant 3-way interaction underscored the interdependence of these variables. Notably, all pairwise interactions demonstrated substantial effects. The combination of group selection method with either group number or layout orderedness significantly influenced both completion time and operational efficiency. Strong main effects emerged for each independent variable. Group selection methods showed particularly pronounced impacts, with completion time and operational demands being overwhelmingly dependent on this factor. Both group numbers and layout orderedness independently affected performance metrics, though their effects were comparatively moderated. Post hoc comparisons revealed nuanced patterns. While group numbers M equals 4 and M equals 7 initially appeared equivalent, subsequent analysis showed significant differences between them, though M equals 7 and M equals 10 became indistinguishable. Layout orderedness exhibited clearer thresholds, with S equals 0.8 consistently diverging from lower orderedness levels, whereas S equals 0.2 and S equals 0.5. showed no significant differentiation. These contextual dependencies highlight the importance of considering variable interactions rather than isolated factors in optimizing system performance. Figure shows the NASA TLX subscores and SUS scores for the 3 methods. Homebon-Ferroni corrected post hoc t-tests were conducted to compare the subscores between the EC method and the CC methods. The EC method showed significant improvements in overall NASA TLX and SUS scores compared to the CC methods. NASA TLX subscores The EC method had higher mental demand than the CEC methods, p less than 0.05. No significant differences in effort and frustration subscores between EC and CC2, p equals 0.78 and p equals 0.061, but significant differences between EC and CC1, p less than 0.001. The EC method showed better performance in other subscores. In summary, we proposed a multi-objective group selection framework with probability permutation enabling rearrangement of target objects. We introduced a probability propagation algorithm based on two strategies to update the grouping probability to determine the grouping priority of the remaining objects, and a position rearrangement algorithm based on the grouping probability to relocate the target objects to reduce layout randomness and make the next selection round easier. We also conducted ablation experiments and an empirical user study to validate our PwP method's effectiveness and usability. That's all for our presentation. If you have any questions, please contact us. Thank you for your attention.